Good afternoon, everyone. Thank you for joining the seminar. Today, I will be present my research, my previous research and recent publications about flood risk assessment and mapping using GIS-based spatial analysis in the wetland region of Bangladesh. It's called Sunamganj District. So, currently, I am working as a senior GIS analyst and at Spectre, and so delve into my presentation. So in the current era of climate change marked by global warming and extreme weather events, flash flood emerged as one of the most severe natural disasters, causing significant loss of lives and substantial social and economical damages. So first of all, we have to know about what is flash flood. The hydrological event occurring within a few hours of intense rainfall or rapid snowmelt or glacial lake outburst or embankment failure causes rapid rise of water level in a certain area is called flash flood. So especially in Bangladesh is a flash flood prone area due to the rapid formation of cyclone. Here you can see the geographical location of Bangladesh. Here is the Bay of Bengal, which is a funnel shape. So the air circulate this area and formate cyclone rapidly, and the route of the cyclone, like inlet up here, we can see inlet up here because here the Himalayan region are situated. So the Himalayan mountain blocked the cloud and sent them to the Bangladesh and causes rapid rain. So flash flood happened mostly in monsoon period, and monsoon period flash flood are actually very daily event for our country, but we assess the flash flood in northern region of Bangladesh during pre-monsoon period. Uh, as we know, flash flood in monsoon period in Bangladesh are less devastating because in this time farmers, especially farmers, did not cultivate any kind of crops. But the last few decades or last few years, we observed that here uh, uh, the flash flood happened in pre-monsoon, especially from May to June in Bangladesh. So these are more demoralizing or causes economical losses in Bangladesh in a agricultural perspective. So this happened due to the global warming or global climate change, and that induces climatic cyclone circulation. So the highest rainfall in the world experience just up of the of my study area here in Cherrapunji, uh, about 11,000 millimeter in a year. So it causes the flash flood in our study area. So our study area is called Sunamganj District. It's a second level administrative of Bangladesh, and then we divided it in 11 upazila. We call it upazila. It's the third level administrative. So those are Dharmapasha, Tahirpur, Jamalganj, Sulu, Derai, and Dakshin Sunamganj, Sunamganj Sadar, Bishnupur, and Dawan Bazar, Chatak, and Jagannathpur. So why this study area? This region we call actually a Howar area, and it's in English term it is a wetland, and here in the study area 400 wetland located, which are actually cover 19,000 square kilometer, and also 23 transboundary river are crosses in this area from upper region called India. So regardless that more than 90 million people living in this region, those are encountered the diverse effect of flash flood. So we decided to conduct a multi-index model in this study area and create a flash flood risk map. So our primary aims was to assess the risks of flash flood using a multi-index approaches and to identify risk zone in the study area. Especially, we aimed to determine flash flood risks using various indicator, conduct a comparative study of this indicator, and analyze socioeconomic parameter and create a risk zonation map finally. Now methodology. So here is a overview of our methods. It's a framework. The four indexes we can see: hazard index, exposure index, sensitivity index, and resilience, and their variables. And then we overlay them in a PCA method, principal component analysis, to assess individual indexes, and then create final risk map. So for conducted research data we have used, we use secondary data, mainly satellite image, water level data, rainfall data, and demographic data from different sources. So we used various data sources for collecting secondary data, like Bangladesh Water Development Board, Japan Aerospace Exploration Agency, Bangladesh Bureau of Statistics, European Space Agency. So here we collected rainfall data for 3-hour interval, water level from 10 station of Bangladesh Water Development Board, and for 5 years, especially those years are experienced for first flood, 2002, 2007, 2017, 2019, and 2022, and then 2020, and then 2022, that is not considered for our study area. Even we have experienced a cyclone in this week actually, called rainfall. Okay, and then and like precipitation data, water level data, we collected precipitation data from Bangladesh Water Development Board, and then data from Advanced Land Observation Satellite (LS), and then actually we extracted drainage pattern, slope, and then topographic wetland index from the dam data. And again, demographic data are collected from Bangladesh Bureau of Statistics, and finally the satellite image Sentinel-2A satellite data are collected from European Space Agency, and then we classified the satellite data to extract our various parameter. So this is our data. And now the data analysis technique. So first of all, hazard index analysis. So it's a popular equation we used. Decay coefficient model. It's a popular equation for calculating hazard index. So here the lambda means the decay coefficient actually is 0, because we calculate the flood depth for only one time, and so the equation generalized at water level minus dam. So we calculate for individual years and then average them for calculating the hazard index. Then exposure index analysis. Uh, the variables are elevation, drainage pattern, rainfall, soil moisture. The equation from following equation, we used the slope from dam using the ArcGIS tool. Actually, most of the study conduct in ArcGIS environment, and then hydrological analysis like watershed delineation, then stream flow and stream water are conduct hydrological analysis in ArcGIS. They calculated the drainage density by sum of length of the stream and divided by area, and then the rainfall data we interpolate them using the green method, and the deviation are showing using that. And the dam soil moisture, actually it's called topographic wetland index, wetness index, which is calculated from flow accumulation and divided by slope. So then for calculating sensitivity index, we used geomorphology, wetland, vegetation, build-up area, agricultural land, and demographic data. So this analysis is actually based on satellite image. First of all, we collect Sentinel-2A data, then the band of blue, green, red, and infrared ray, and dam are composite, and then isocluster algorithm perform to extract the geomorphic feature, and then wetland ratio index, water ratio index are calculated by this equation using green, red near infrared, and shortwave near infrared band. Those are actually band 3, band 4, and band 8, band 12 for Sentinel-2A, and then calculated normalized differences, vegetation index, and DBI, and for build-up area we calculated NDVI, and again maximum likelihood supervised classification are conducted for extracting the agricultural land in our study area, and some inferential statistics of population density or depending population calculated for conduct sensitivity analysis. And lastly, for calculated resilience index analysis, we use literacy rate, housing structure, poverty rate. Those data are collected directly from Bangladesh Bureau of Statistics report 2011, Community Book of Sunamganj District, and the Poverty Map of Bangladesh 2016 report, and then interpolated them according to Upazila wise or union wise. A union is a 4-level administrative of Bangladesh, and then we after analyzing all of the data, we conduct a PCA for individual indexes. Actually, I would like to talk about principal component analysis. So what is principal component analysis? The principal component analysis is a statistical technique that transforms correlated variables into a set of undercorrelated component and capturing the maximum variance with fewer variables. So we can actually overlay our data many others method like AHP, analytic hierarchy process, but to conduct AHP we have to know about the influence ratio of the study area of different variables, or some recommendation from a wise scientist, but we don't have that access. So that's why that is a factor for selecting PCA, but we have another reason for selecting PCA method because it's a data driven approach. PCI is purely data-driven approach, which means it relies on inherent patterns of the within the data we used previously. It did not judge the data subject. So this is crucial for our study, and it's handle the high dimensionality. And another one is the it's capture the maximum variance. So we don't have to rely on the influence factor. So here is the PCA eigenvalue result after conducting principal component analysis. So you can see the for exposure index, elevation have highest influence, for sensitivity index, geomorphology have highest, and for literature index, for resilience index, literature rate have highest influence ratio. And lastly, after analyzing for 4 indexes using PCA, we classified them for classes using natural break method in ArcGIS environment. And then because there has no rules for suspectability in previous study in literature review, so we actually generally break them in a natural way, a natural breaks method, and then prepare our flash flood risk map using this equation: hazard into exposure plus sensitivity minus resilience. So now dig into our result. So first of all, hazard index. From rainfall analysis, we can see the combined flood depth, our analysis in the figure, and then and we classified as like low risk below 0.9 meter flood depth, moderate risks 0.5 meter to 1.8 meter, and high risks 1.8 to 3.61 meter, and above 3.6 meter are very high risks. So our result indicate an average flood ranging from 3.61 to 8.74 meter, which is a very high risk, particularly in the western side of the Upazila of the study area. And in this table, we also can see that the flood depth are increasing yearly, day by day. So it's increase the vulnerability of the study area regarding flash flood. So now exposure index. For calculating exposure index, variables results shown in this slide. The elevation map reveal that most of the study area has low elevation and shallow gradient slope here in the slope map, and then most of the study area are below 5-meter elevation with a shallow gradient slope like 0 to 3 degree, and then but highest slope is 55 degree, which is most in this area, which is actually mountainous, but it's cover a short, very short area. So that is not affect so much. And then drainage density, we can see here is here in this study area across a Surma river, and around the Surma river, and here some wetland we can found, and those in those areas especially drainage density is higher. So, and about 2 kilometer is 2 square kilometer, more than 2 square kilometer, which indicate more surface runoff associated with high risks and very high risk flash flood zone. And the higher drainage density show impermeable subsoil materials, sparse vegetation, increased runoff. That's why it make the study area very high risk. And the rainfall map, uh, in the rainfall map, the map T, we can show that see that the heavy down pour of rainfall from the north, because of I already told about the cyclonic phenomena, orographic rainfall actually we call, and the higher topographic. You can see in this image the whole study area cover actually the higher topographic wetland index, and the mean is 11. So it's considered that the higher it's considered the study area is vulnerable according to the topographic wetland index. And then we conduct a PCA of them, the correlation matrix of exposure index. So here you can see that the strong correlation between elevation, slope, topographic index, and drainage density. And in the index, the highest significant value represent topographic wetland index. So, and we also can see that the final result map, the topographic index actually dominating this map. So now for final result of exposure index, our study identified that the area with low gradient slope, higher drainage density, and higher topographic value are observed to be a higher risk of flash flood. And in addition, exposure map provide that a high risk zone was mainly developed in the higher drainage density area with low gradient slope and low elevation. So the other specters are also present here. The spatial distribution of flash flood risk exposure was high, especially in northeastern part, and low in northwestern part of the study area. So for calculating sensitivity index, 6 geomorphological features such as deep depression, shallow depression, flood lane, and active channel, and lowland and plain land were identified, and then assigned risk class according to like high density of deep depression and shallow depression, floodplain, and active channel was responsible for high risk zone. So the final outcomes of geomorphological look like this. And then uh, the figure of water ratio index, which show the high mean of water ratio value, indicate deep water, which actually is situated in deep water. Here is the actually the Haur, mainly the wetland are situated in this red region. So those represent the high water ratio value. And then the NDVI value, actually the NDVI value represent high vegetation or low vegetation. It's range 1 -1 to +1. The the more positive value represent more vegetation. So the vegetation actually slow down the runoff, and it's make the region less vulnerable. And the high and low vegetation is high vulnerable to flash flood. and then the normalized differences build-up index. So for calculating build-up index, we already used equation from satellite images and found that the build-up area are sparsely distributed in this study area, but in the lowland area, there we can see that there have no build-up or settlement. So most of the build-up area in upper region or highland, and those are more resilient, more sensitive to the flash flood. And lastly, the agricultural land. Uh, so low elevated agricultural land in the study area is most vulnerable to flash flood, according to our literature review. The middle part of the Sunamganj area here, very high risk zone so for potential damages to agricultural land. So then the population density, which is also a parameters for calculating sensitivity index. So the higher population density, the higher flood risk, and the sex ratio of study area almost equal actually. So the which mean more than 50% of population had higher risk because of women and children could face more vulnerability due to the flooding period. And it was found that flash flood affected densely populated area more than sparsely populated area. So the figure in this figure we can see that the Dharmapasha, Satok, and in those region are more vulnerable uh, according to the flash flood sensitivity index. So here we can see the depending population. There's another variable, the last variable, and the depending population aged from 0 to 14 and above 65 years old are old. So most of the percentage of dependent population in the study area average is 52. So we can say the half of the population are dependents, and that's why most of them are vulnerable. And we can see the northern Upazila has higher dependent population, so these are more vulnerable to and more sensitive to the flash flood. And then finally the sensitivity index correlation matrix, which we can see that the water ratio and geomorphology, NDVI, and water ratio index, NDVI and NDVI, and population density have a strong correlation among themselves. And last, the final map output of sensitivity index, and these area which are actually western part of the study area are more sensitive to the flash flood than eastern part. And water ratio index value in the deep or shallow depression containing area such as Dharmapasha, Tahirpur, Jamalganj, Sallu, these are more sensitive because the Haur oriented region, those are Haur oriented region. And then uh, resilience index, we considered actually structural capabilities and then non-structural capabilities for calculating resilience index. So structural capabilities related to settlement and infrastructure abilities, and non-structural factors related to livelihood. So we considered for structural resilience, housing structured, and for non-structural resilience, we evaluate literature rate, poverty level. Okay, so at first literature rate, here we can see that the lower literacy rate at the mass level resulted unconsciousness of severity of flash flood and less willingness to adopt precaution. So the significant amount of people below the poverty line showed their inability to fight against flash flood at the constructive or non-constructive level. So the average literature rate in the district of Sunamganj was 35, which is very low, and which makes the region less resilient against flash flood. So low literacy rate found lack of education, institutional education in this region. Actually, this region is mountainous and full of wetland. So that's why the communication system is not well established, and that's why it is we can see the educational institution, lack of educational institution. And then poverty rate. The poverty rate scenario showed that Tahirpur, Jamalganj, Derai, and Sallu Upazila had highest poverty rate over 22, uh, and especially Sallu Union, this union uh, had highest percentage, above 60%. The overall poverty condition indicate 26% of inhabitants of the study area live just below the upper poverty line, so they have poor resilience. And then the last one, housing structure. The housing structure of the study area consists four type: pakka, semi-pakka, kacha, and jupri. Okay, so let me elaborate that. Pakka is made of actually concrete, and then semi-pakka is half concrete, and actually the roof is not well structured. It made of tin or wood. Then kacha are completely made of wood and tin, and then jupri, the houses condition are actually they are made of wood leaves, wood and leaves of some plants. So those are actually more vulnerable to the flash flood. So according to the Bangladesh Bureau of Statistics report 2011, more than 60% of housing structure was kacha and jupri, and flash flood could quickly destroy the kacha and jupri houses because people are almost exposed to disaster without any solid protection. So Sallu, Dharmapasha, Tahirpur, Jamalganj, Terai, and Dakshin Suramganj had more than 80% of vulnerable houses, and still the percentage of Pakka and semi-Pakka constructed houses in the Sunamganj in the study area could be much higher. So Jagannathpur and Chhatak, this region have higher percentage of Pakka houses. So that's why those area are actually less vulnerable and, and less fragile to the flash flood. So here is the correlation matrix of resilience index variables. So here we can see the only dominating factor is housing structure in for this resilience index. So finally, the resilience index, which is actually interpolated according to the subdivision of the district, or we call it as Upazila. So the resilience index maps show that Jamalganj, Taipur, Dharmapasha, this region are very high and very high risk zone for the flash flood because there is Upazila or Haur-based region, and more than two-thirds of housing structure are Kasa and Jupri, and the poverty status was moderate to very high, and less than 40% of people had literacy rate, which is also resultant in ignorance and low to very low economic prosperity, resulted less ability of a fundamental right, and as well as weak resilience. So lastly, the flash flood risk map, our final map, was generated by integrating four indexes: hazard, for exposure, sensitivity, and resilience. So the table show that now about 40% of the study area have a high probability of flash flood, and while moderate, low, and very vulnerable area are 18%, 4%, and 38% respectively. And the risk assessment map indicate that the study area western part and middle part are more susceptible to flash flood than eastern flood, because western part has characteristics of very low elevation, lower degree of slope, high drainage density, lower income status, poor housing structure, and the geomorphological feature and vulnerability of human social condition causes the higher risks of higher risks in the western and middle zone of the study area. So beside, the flash flood risk map showed the high density zone in deep shallow depression in those areas which are actually covered by wetland. So highest number of historical flood actually happened in this region comparatively the western part. So after conducting our research, we go to our study area for ground truthing. This process actually involved field survey, collecting water level measurement, assessing local topography data, soil condition and drainage system, and interacting with local community to understand their flood experience. Like people of high risk zone, uh, like this region, um, hardly cultivate one time in their land, but in the western part, which are the less risk zone, cultivate three times in a year. Oh, okay. So the data systematically gathered from 36 point within the study area during our fieldwork, and this rigorous data collection process was conducted to ensure the accuracy, reliability of the risk assess, while spatial distribution of this data are visualized here in this figure. So the overall accuracy of this of our study is 0.86, and the kappa coefficient is above 80%, so which is actually satisfiable. And during the ground truth, we actually experienced another flash flood in July 2022, when we captured some photographs like the devastating effect to show the devastating effect of flash flood. Like we can see the no access of pure water, and then the communication system is completely disrupted. So and finally, based on the risk assessment, we ranked Upazila wise of our study area. So in the first rank, Dharmapasha, we can see the Dharmapasha, then Sallu, Terai. So based on the risk zonation map, Dharmapasha Upazila occupied more than 60%, and followed them to Sallu, Terai. So this is the main outcomes of our study to conduct some measures. So the key finding: the western part of the Upazila showed very high risk zone. The flash flood risk exposure was very high in the western part and low in the eastern part. The western part of Sunamganj was more sensitive to flash flood than eastern part, and the eastern part and northern part showed high resilience. And our findings show that almost 40% of the study area have a very high risk zone. So according to our assessment, we suggest some mitigation approach in the study area, develop early warning system, actually in community-based early warning system, and infrastructure improvement like elevated the roads and accessible and set up some oil for access to fresh water, and community-based adaptation, afforestation and deforestation, and most importantly, educational initiative and integrated water resource management, and finally the climatic resilience agriculture. And and this paper is already published. We can see in this link. So that's all from my study. Thank you.